So again, we have two wires parallel to each other, and one carries current I1, the other carries current I2. If you look at the current through wire number 1, the magnetic field lines form these circular patterns around that wire. One of these circles happens to intersect with a point on wire number 2. Right at this point, the magnetic field is B1, okay, and it's pointing tangent to this circle. Right at this point, that's pointing upwards. That's what's labeled here B1. It might seem a little strange that we're labeling the magnetic field B1, given that it's a point on current number 2, but it's the magnetic field caused by current number 1, and current number 2 just happens to be in that field. If it's in that field, it will feel a force. What's the force? F is I times L cross B. L, remember, as a vector, points in the direction of the current. In this case, it would be I2, feeling the magnetic field B1 caused by current I1. So the cross product of a vector pointing in the direction of the current I2 with this magnetic field B1 will give you the force, and the direction of the force will be, well, it's a little messy here, but you can see the force is pointing from the wire number 2 towards wire number 1. In other words, the current I1 creates a magnetic field. This other current feels a force because it is in the presence of this magnetic field due to current I1, and that force is attractive. I2 is attracted to I1. Now you can go through same kind of analysis. You could say, well, current I2 creates its own magnetic field, so those are the field lines that are concentric circles around this wire. One of these circles happens to intersect current I1. The direction of the direction of the magnetic field caused by current 2 is in this direction, using the right-hand rule that we just talked about. That means for this field line right here that I'm tracing out, right at this point is pointing downwards. And the vector L in this cross product for wire number 1 is pointing in the direction of I1. So L points in this direction, the magnetic field at the position of wire 1 points down. The cross product is, and this equation up here tells you there will be a force acting on wire 1, pulling it towards wire number 2. Okay, now this is a lot to try to understand. It's a messy picture and there's a lot going on here, but give it a go. Try to really understand the significance of what all this stuff is. So at the end of it, if you combine these two equations, you draw a picture like this, and you can argue that the force is going to be attractive. Wire 2 gets pulled towards wire 1, and wire 1 gets pulled towards wire 2. The forces will have the same magnitude, as you would expect. That's Newton's third law. For every action, there's an equal and opposite reaction. Okay, if 1 pulls on 2 with a force, 2 pulls on 1 with a force of the same magnitude, opposite direction. The magnitude of the force, combining these equations and keeping these directions in mind, turns out to be this. So mu naught, again, is just a constant. L is going to be the length of each of these wires. We're assuming that they're the same length. And I1 and I2 are the currents. D is the distance between the wires. So not surprisingly, the more widely spaced the wires are, the bigger D is, the smaller the force is. And also not surprising, if you increase I1 or if you increase I2, or both of them if you want, then you're going to increase the force. If you increase the length of each of these wires, you'll also increase the force. Okay, so that's the equation that tells you how to calculate the force between two parallel wires that are carrying currents I1 and I2, both of length L, with a distance d between these parallel wires. So we've already argued that if the currents are parallel to each other, going in the same direction, then we have an attractive force. You can also show, going through a similar kind of argument as what we just did, that if the currents are anti-parallel, meaning maybe I1 is going in the same direction, but I2 is going in the backwards direction, you can show for anti-parallel currents that you have a repulsive force. Still the same magnitude, this equation is still the right equation, it's just instead of an attractive force, you have a repulsive force. This is a little bit like, if you remember way back when we talked about Coulomb's law, the electric force between point charges. It's a similar kind of equation. It's a little bit different though. There was no L. The distance between the charges was squared in that other equation. And instead of currents, we had electric charges. So it's similar, but there are obviously differences between this equation and the Coulomb force. Go back to the beginning of chapter 20, I believe it was. Compare this to the expression for the Coulomb force, and you'll see how it's similar and also how it's different. Okay, so moving along. If you have a loop of wire, okay, so this is not a magnetic field. Well, the pink lines are the magnetic field lines, but this loop here is a ring. So you bend a wire into a circle, you pass a current through it, and but that current creates a magnetic field. These are what the magnetic field lines, as it turns out that these are what the magnetic field lines look like. They're closed loops. They're not circles. I mean, the ring itself might be, the wire might be a circle, but the magnetic field lines are not actually circular anymore. They're a more complicated shape, but they do have that kind of closed loop structure to them. If you have, instead of a single loop, you have a little bit of a helix. This is what the magnetic field tends to look like. So the magnetic field lines tends to be stronger because the field lines are close together inside the coil. They tend to be a little bit weaker outside the coil. If you have a coil that's a little bit longer, you get an even stronger and more uniform magnetic field inside the coil. And the outside the coil, you still have a magnetic field, but notice the field lines are spaced further apart. The magnetic field tends to be very weak outside, very strong inside. And if you make the coil even longer, you get a stronger and even more uniform magnetic field inside the coil. And outside the coil, the longer this coil becomes, the smaller, the weaker the magnetic field tends to be in the space outside the coil. Okay, so we're not going to go through a full analysis of the magnetic field for a helical current-carrying wire. And by the way, this is called a solenoid. Okay, a solenoid is a long, tightly wound wire coil that carries some current. Okay. So if you have a solenoid characterized by this property that it has little n loops or turns per unit length. Okay, so what does that mean? Well, maybe there are, I don't know how many there are, maybe almost 10. Or we'll say there's 10 turns here. And if this was 1 centimeter long and you had 10 turns, little n would be 10 divided by 1 centimeter. Okay, so that's what we mean by little n, the number of loops per unit length. So it turns out that if the solenoid, this helical shaped wire, is very tightly wound, it turns out, to a good approximation, the magnitude of the magnetic field goes like this. The constant mu naught again times n, and the n again is this, the number of loops or turns per unit length, and by per unit length I mean the length of the whole coil itself, not the length of the wire going all the way around, but just the length from this point in a straight line to this point. Okay, so B is mu naught times that n multiplied by the current. And the field is approximately uniform inside the coil. So why might you care about something like this? Well, you've probably heard of MRI. MRI stands for magnetic resonance imaging. And it's a diagnostic tool used in hospitals. Maybe you've had an MRI taken yourself. If you have, you will recognize what's going on in this picture. So the patient is laying down and will be put inside this tube. And what the tube is literally the inside space around which you have many thousands, hundreds of thousands of turns of a wire which carries a current and therefore creates a really big magnetic field in this space. Okay, so inside this tube is a really strong magnetic field caused by the fact that around the periphery, you don't actually see the coil, but around the periphery of the tube is a helical coil of wire carrying a current. Now, I'm not going to tell you how magnetic resonance imaging works. That's very complicated. But one of the things it requires is a really strong magnetic field. And that's how the magnetic field is generated. Okay. So what else do we want to do? Now that we know about magnetic fields, and we know something about electric fields as well, we could do quite a bit with this if we had the time, but we don't have the time. So we're just going to do a little bit. So it turns out that the properties of electric and magnetic fields are completely described by a set of 4 equations, and these are called Maxwell's equations. If you're curious, you can look in chapter 29. And the significance of Maxwell's equations is they predict the existence of electromagnetic waves. And that's what light is, that's what radio waves are, and so on, all the electromagnetic waves. They're electromagnetic waves. Okay, what does that mean? An electromagnetic wave has particular properties. So this is a complicated picture here. It's in the textbook somewhere, I forget in which chapter. You'll be able to find it there in the chapter on, maybe it's chapter 29 on Maxwell's equations. So imagine you have a line of points along the x-axis. And if you have an electromagnetic wave, which is propagating to the right along the positive x-axis, what's actually happening? Okay, we're considering, as I said, just a single line of points in the direction that the wave is moving. So what's happening is you have at, let's say, this point here, you'll have an electric field. The electric field may be pointing in the positive y direction. The magnetic field, there's a magnetic field present at exactly the same point, and it's directed or pointing in the positive z direction. Okay? At this point over here, you have an electric field pointing up along the positive y direction. It's a little bit bigger than it was over here. And you have a magnetic field, which is pointing again along the positive z direction. Okay, so at a given point in time, at a given moment in time, these are what the electric and magnetic field vectors look like for an electromagnetic wave which is propagating along the positive x-axis. Now that's just one moment in time. These are waves. So remember when we studied waves earlier in the course, we talked about, the fact that you have a sinusoidal wave. So this is an example of an electromagnetic sinusoidal wave. The electric fields and the magnetic fields form these kind of sinusoidal patterns, which tell you something about the magnitudes of these vectors. And these peaks and troughs, both for the electric and the magnetic field, are both moving with a constant velocity to the right, in the direction that the wave is propagating. And as the wave propagates along, and the crests and troughs go by any given point along the x-axis,